Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 10th, 2025, just yesterday. This paper introduces a new method that significantly improves video quality, cutting the Frichet video distance, a key metric for visual fidelity, from 364 down to 243. The paper is titled Geometry Forcing, Marrying Video Diffusion and 3D Representation for Consistent World Modeling. And it offers a really clever way to make generated videos more stable and realistic. The core idea is to force a video diffusion model to learn 3D structure by aligning its internal features with a geometry-aware model. So this first figure really breaks down how this geometry forcing method works. On the left, it shows a pre-trained model that understands 3D geometry, a visual geometry grounded transformer, or VGGT, being used to guide the main video model. And the results are dramatic. The baseline video quickly becomes incoherent, while the geometry forcing video stays stable. But the most telling part is the 3D reconstruction. The baseline's internal features produce a jumbled mess, while their method creates a clean, recognizable room, proving the model truly learned the scene's structure. This next figure provides a powerful visual for that idea of consistency. What we're seeing here are frames from different models, all trying to simulate a full 360-degree camera rotation in a room. The baseline models in the top rows, well, they just fall apart. The scenes become distorted and lose all sense of place. But the bottom row, using geometry forcing, is remarkably stable. It smoothly pans around and ends up right back where it started. This directly relates to a metric called revisit error, which simply measures how well a model returns to a starting point. And this table provides the hard numbers to back up those impressive visuals. It compares geometry forcing against other methods on the Real Estate 10K dataset for both short and long videos. For the long, 256-frame videos, the results are stark. The model drops the Frichet video distance, our visual quality score, from 364 down to 243. It also scores best or second best on nearly everything else, including reprojection error, which is a key score for how well the model's internal 3D understanding holds up across different views. So the natural question is, why does their specific method work so well? This table shows an ablation study, which basically tests each component to see what's most important. The model is guided by two objectives: angular alignment for feature direction and scale alignment for feature magnitude. Using just angular alignment already improves the Frichet video distance score a lot, but combining both gives that best result of 243. And look at the last row. Using a simple mean squared error, a standard way of measuring differences, makes things much worse, showing their two-part approach is essential. Building on that, this next table explores a different question. How should we integrate this geometry information? Is it better to guide the model from the outside, or force it to learn the structure internally? So they compare their method against a control net, which is a common way to provide a model with extra external guidance. The results are really clear. While using the control net improves the Frichet video distance score to 275, their internal alignment method is much better, achieving that final 243 score. This shows that making the model truly learn the 3D structure is more powerful. Alright, so the quantitative metrics tell a clear story. But what about human perception? This table shows the results of a user study where people rated videos on a scale of 1 to 5. They looked at three things: how well the camera movement was followed, the consistency of objects, and the overall scene continuity. And the results are just as decisive. Geometry forcing scores above 4.4 in every single category, far surpassing the other methods. This really confirms that the improvements aren't just in the numbers. They create videos that are noticeably better to the human eye. So in the end, both the hard data and the human feedback point to the same conclusion. The core idea of geometry forcing, which is to guide the video model's internal learning process to align with a true 3D understanding, is incredibly effective. It bridges the gap between just generating pixels and actually modeling a consistent world. This approach leads to videos that are not only more realistic, but also maintain their sense of place over long durations. And that's our roundup for this week. Thanks for tuning in.